Hey guys, this is Mrs. Hardin, and this is Pre-Cal, Chapter 2, 2.6, Zeros of Polynomial Functions. Now, I mentioned that last presentation, and hopefully you remember from last year, that the zeros of a function are where it crosses the x-axis, and finding the zeros can help us graph complex or difficult polynomial functions. Our life application for the chapter remains the same. The student U will be aware of angles in creation. Just as each geometric angle has a precise measurement when properly aligned with a measuring tool, so too the angle that the student's life takes will have a precise direction if he is properly aligned with God's Word. We know that God is a God of precision and precise measurement, and not only in mathematics, but also in conduct and how we're to treat one another. Our lesson objective is that you, the student, will find the zeros of polynomials with rational, conjugate real, or conjugate complex zeros, and find polynomials that satisfy given conditions. So let's think. How do you factor 2x squared minus x minus 6? Well, we're going to factor that by grouping. Hopefully remember how to do that. You take your 2 times your 6 and get 12. And then you think, what are all the factors that when I multiply, I will get that negative 12 there. But when I add, I will get a negative 1. And hopefully you realized, or you've already seen, negative 4 and positive 3. When multiplied, give me a negative 12. But when added, give me a negative 1. And then we will factor by grouping here and here. And we end up with x minus 2 times 2x plus 3. And hopefully that is a review for you. So our zeros are at 2 and negative 1.5. And the way that we find our zeros is take each of our factors and set those equal to 0. Since we want our whole thing to be 0 here. And then we solve for x. And here we get x equals 2. And here we get 2x equals negative 3. Divide both sides by 2. And you get x equals negative 3/2, which has been translated into decimal here, negative 1.5. 0 is 2 over 1 and 3 over 2. Notice, and I wrote on the screen there, so let me see if I can erase that here. Notice that the numerator in each of our zeros here is a factor of the original constant, of the original 6, negative 6, and the denominator is a factor of the leading coefficient here, 2 and 1. You will need to pay attention to that. That's going to come into play here in a little bit. So, here's the future. Now, we need it now. Find the possible rational zeros of p of x equals 4x cubed minus 3x squared plus 7x plus 5. So the first thing that we're going to do is list all the possible zeros. And to do that, we need the factors of the constant, which is 5. That gives us plus or minus 1 and plus or minus 5. And the factors of the leading coefficient, 4. And our factors are plus or minus 1, plus or minus 2, plus or minus 4. And when finding all the possible rational zeros, we are going to use those C and D factors here, constant and leading coefficient factors, and write all the possible different rational zeros. So we have plus or minus 1 over 1, plus or minus 5 over 1, plus or minus 1 over 2, plus or minus 1 over 4, and plus or minus 5 over 2, plus or minus 5 over 4. So those are all of our rational zeros. 1, 5, 1/2, 5/2, 1/4, and 5/4. So each of these could possibly be a 0. Now we could plug each of these into the equation and see when we plug these numbers in what gives us a 0 remainder. That's one way to go about it, but that might take us a little bit of time. So a rational root theorem looks a little wordy and chunky, and it says this. In a polynomial, essentially, remember this is just our definition for a polynomial, where we have a coefficient and an x to a term. So our first coefficient, an x to the maybe fourth term. And then we have x to the 4 minus 1, which is the third term, and x to the n minus 2, or 4 minus 2, which is the second term. So this was our definition here of a polynomial. So in this polynomial, where the coefficients are integers, and if C over D, the factors of your constant term over the factors of your leading coefficient, is a reduced rational root of p of x equals 0, meaning that C and D are relatively prime, they're reduced, then C is a factor of our constant term, and D is a factor of the leading coefficient. So when we're looking at our rational roots, in order for a number to produce a zero, a root, if you will, then C must be a factor of the constant term and D must be a factor of the leading coefficient. So let's find the roots of 6x cubed minus 5x squared minus 2x plus 1. Okay, our possible roots, plus or minus 1 over 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6. Ooh, I went really fast there. Remember, we got that from our factors of C all over our factors of D. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And that's where we got these possible roots. All right, once we know all of our possible roots, we are going to pick one to use for synthetic division. We could start with these whole numbers here, these integers, and plug those in to see what gives us a zero root. And we're going to start with 1. One of our zeros being 1. And when we conduct synthetic division, we get a zero remainder, which tells me 1 is a zero of that polynomial. When we factor out x minus 1, we're going to write a reduced polynomial here, which is 6x squared plus x minus 0. You should be able to factor this like normal using grouping and factoring by grouping. We get x minus 1 times 3x minus 1 times 2x plus 1. We'll then set each of those equal to 0 to find the 3 zeros. So x minus 1 equals 0, 3x minus 1 equals 0, and 2x plus 1 equals 0. And then we'll solve for x, and when we do that, we get x equals 1, x equals 1/3, and x equals negative 1/2, which meets our definition, that the numerators are factors of that constant term, and our denominators are factors of our leading coefficient. So we know that those answers are logical. If the leading coefficient of a polynomial is 1, then all of our rational roots must be integers, because the only factors of 1 are positive and negative 1. And if our rational roots are C over D, then all of our roots are all over 1, which means they must all be integers. Those integer roots must be factors of C, the constant term. So here our leading coefficient is 1, so we just need to list or worry about the factors of 14, because 1 on the bottom is just an integer. So our possible rational roots, plus or minus 1, 2, 7, and 14. Again, we could plug these in and find out which one gives us 0, but that might take a while. We know that positive roots would have to be eliminated, because positive numbers, no positive number is going to make this 0. So we know our root's going to have to be a negative number. So just to save time, I'll tell you, negative 2 is a root. So let's try negative 2 here. If we did synthetic division and divided by our negative 2, or x plus 2, we get x plus 2 as a factor, and this would be our reduced polynomial. We're then going to factor by grouping and end up with these 3 factors. To solve for 0, to find out our zeros, we'll set each of these factors equal to 0. And we get that our zeros are negative 2, negative 7, and I and negative I. Now just a reminder how we got that. When we subtracted 1 from both sides, we got negative 1 equals x squared. To eliminate that square term, we've got to take the square root. And you cannot take the square root of a negative number and still have a real number. So we have to say that these are imaginary. So the square root of negative 1 is 1i, or plus or minus 1i. And since we don't usually write the 1, it's just plus or minus I. It is possible that a polynomial has no rational roots, so do just be aware of that. Let's talk for a minute about the conjugate root theorem. If p of x is a polynomial with real coefficients, and if z equals a plus bi is a root of that polynomial, then its conjugate, a minus bi, is also a root. So just keep in mind, if you end up with an imaginary number as one of your roots, its conjugate, which is like its opposite, is also a root. Continuing with our conjugate root theorem, if p of x is a polynomial with rational coefficients and a plus c square root of b is a root of p of x equals 0, then a minus c square root of b is also a root. So again, conjugates, if one if one imaginary number, complex number, is a root, its conjugate is also a root. Let's take a look at this example. X plus 4, x to the fourth plus x third minus x squared plus x minus 2 equals 0 has negative I as one of its roots. Find the other roots. Well, we know because of the conjugate root theorem that positive I is also a root of p of x. X minus I and x plus I are both factors of p of x. So how will we find the others? Well, x minus I and x plus I are both roots, and we're going to use this to represent the other factors, roots that we don't know just yet. When we FOIL and start to work our way backwards, we get x squared plus 1 times q of x equals this polynomial. So if we divide our original polynomial by x squared plus 1, we'll find out what's left, what our q of x is. We're going to use long division for this, and I'm going to go through this really quickly. I'm not going to explain it, but it's the same process as regular long division. Don't marry stinky boys. Divide, multiply, subtract, bring down. Don't forget that when you're subtracting, you need to distribute that negative sign to everything inside the parentheses. If you need to pause and go through this slowly, you may do so. And if you need me to explain this in more detail, make sure that you ask me next class. We end up with a remainder of 0 after long division, and our reduced polynomial is x squared plus x minus 2. Now, according to our fundamental theorem of algebra, every polynomial of degree, remember degree is just the exponent with your variable, greater than 0, with complex coefficients, has at least one root in the system of complex numbers. Also, every polynomial of degree n, let's say 4, with complex coefficients where n is greater than 0, can be factored into n linear factors. So using 4 as an example, every polynomial, a fourth degree polynomial where 4 is greater than 0 can be factored into 4 linear factors. A polynomial of degree 4, where 4 is greater than 0, has exactly 4 roots. Now we can replace that n with any number as long as n is greater than 0. Now these may not be 4 distinct roots. You can have a root that's repeated with multiplicity, but there are going to be 4 roots and at most 4, or at most n, whatever the n is. I'm using 4 to represent my n. So find the zeros of p of x. We know that we should have 4 roots, whether they're distinct or not. So let's find our rational roots. First, using c over d, we find our factors of that negative 4 all over the factors of 1 are plus or minus 1, plus or minus 2, plus or minus 4. We're going to use synthetic division and divide this whole thing by 1. And when we do so, we find out that 1 is a root because we got a 0 remainder. Since 1 is a root, we're then going to write our depressed polynomial, which is positive 4, negative 4x, negative x squared, and x cubed. But then what do we do? Well, we can divide it again, and we get another 0 here. So now we have x minus 1, and 4, 0 term, and x squared. So we have 2 here, and we could do difference of squares to get our last 2 here. So we've got 4 different roots. Now when we write that, we're going to write it as x minus 1 squared and x squared minus 4. It's only look like 2 roots, but we know that it's actually 4 because that x minus 1 has a multiplicity of 2. So in summary, we found the zeros of a polynomial. In this case, the x to the fourth minus 2x cubed minus 3x squared plus 8x minus 4, 4 different factors because of that 4 degree, even though one of them has a multiplicity of 2. Our zeros are 1, negative 2, and 2, and 1 has a multiplicity of 2. Today we found the zeros of polynomials with rational, conjugate real, or conjugate complex zeros, and we found polynomials that satisfy given conditions. If you have any